Assalamu alaikum students. Welcome to lecture 24 of data structures and algorithms. We are going to talk about graphs and we used chapter 8 of book 4 for this topic. Have a look at the definition. A graph G is a mathematical structure which comprises two sets, a set V, the set of vertices or nodes, and a set E, the set of edges. An edge E1 from the set E connects two nodes V1 and V2, both of which come from the set V. If the edges are undirected, we refer to G as an undirected graph or simply a graph. If the edges are directed, we refer to G as a directed graph or a digraph. If E contains both directed and undirected edges, we call G a mixed graph. Looking at the terminology for graphs, two vertices or nodes are adjacent if they are connected by an edge. So if an edge exists between two nodes, they are adjacent to each other. Some people say they are neighbors of each other. Here you can see that A and B are adjacent, but A and C are not adjacent because there is no direct edge connecting A to C. In an undirected graph, each vertex V has a degree, which is the number of edges connected to V. What is the degree of the vertices in the graph shown here? Let me show you how to do this. Look at A. There are 3 edges connected to A, so the degree of A is 3. Find the degree of all the other nodes. In a directed graph, each vertex V has an in degree, which is the number of edges coming into V. In a directed graph, each vertex V has an out degree, which is the number of edges going out of V. What are the in degree and out degree of the vertices in the diagram shown here? Again, let me give you an example. Look at node A. 3 arrows are coming out of A, so the out degree is 3. 1 arrow is going into A, so the in degree of A is 1. Find the in degree and out degree of all the other nodes. A vertex with no incoming edge is a source. So here A is a source because it does not have any arrow coming into it. A vertex with no outgoing edge is a sink. So here C is a sink node because it only has incoming edges. It does not have any outgoing edges. Parallel edges and self loops. In an undirected graph, if two edges connect the same vertices U and V, or in a digraph, if two edges go from the vertex U to the vertex V, these edges are called parallel or multiple edges. I have shown parallel edges with red color in the undirected graph and in the directed graph. Now people might question, why would you need parallel or multiple edges in a graph? Suppose that this graph actually represents flights between airports. So E is an airport, D is an airport, and two different planes at two different times are flying from E to D. So they cannot be shown by one edge. They will be shown by parallel edges. An edge that connects the vertex V to itself is called a self loop, and I have highlighted self loops here with blue color. A simple graph does not have parallel edges or self loops. This means that both the graphs depicted here are not simple graphs. They are non-simple graphs. In a simple graph, we will not have any parallel edges and we will not have any self loops. An important concept related to graphs is the path. A path from vertex V1 to vertex V2 is a sequence of vertices V1, Vi, Vi plus 1 all the way to Vm and then V2 such that V1 is adjacent to Vi, Vi is adjacent to Vi plus 1 and finally Vm is adjacent to V2. The path starts from V1 and ends at V2. The length of a path is the number of edges that constitute it. The length of a path is 1 less the number of nodes in the path. So if the length of the path is 3, it will be composed of 4 nodes. Here you see a path in the undirected graph. This is a path from A to E or a path from E to A. And you can see that it goes from A to B, then from B to D, and then from D to E. Or it goes from E to D, then from D to B, and then from B to A. Since it is undirected, you can move both ways. And here is a path in the directed graph from A to C. It goes from A to B, then from B to D, and then from D to C. The length of both these paths is 3 and the number of nodes constituting them are 4. A path composed of undirected edges is an undirected path. A path composed of directed edges is a directed path. A path is simple if no vertex is visited twice when moving along the path. Look at the undirected graph. I am making a path from A to B. Can I go there like this? I go from A to B, then B to C, then C to D, then D to B. Now this is certainly a path from A to B, but it is not simple because I have visited B twice. Come to the directed graph. I am making a path from A to D. So I go from A to B, then from B to D, then I go from D to A, then I go from A to E, then I go from E to D. So I start from A and I get at D. This is a path from A to D, but it is not simple because I have visited D twice and I have visited A twice. We concern ourselves with simple paths only. Why? Because simple paths are always smaller than the non-simple ones, and we are mostly concerned with simple paths in all our calculations. Cycle. A cycle is a simple path of length greater than 2 that starts and ends at the same vertex. The first thing that you need to understand is that a self loop is not a cycle. Why? Because the length of the self loop is 1 and the length of a cycle is always greater than 2. Then notice that the cycle is a simple path. No node is repeated in a cycle except the first node, which is also the last node. A graph or a digraph is acyclic if no cycle is present. I have highlighted a cycle in each of the graphs shown here. In the undirected graph, we have a cycle from A to A, or you can call it a cycle from B to B, or you can call it a cycle from D to D, or you can call it a cycle from C to C. In the directed graph, we have a cycle from A to A, or you can call it a cycle from B to B, or you can call it a cycle from D to D. Reachability. A vertex V is reachable from U if there is a path from U to V. We say U reaches V. Consider the node A in the undirected graph. It is not directly connected to C, but there is a path from A to C. So I can say that C is reachable from A, or I can say that A reaches C. In an undirected graph, reachability is symmetric. If U reaches V, then V reaches U. So once I have established that A reaches C, I can say that C reaches A because the edges are undirected and I can go both ways on them. In a digraph, it is possible that U reaches V, but V does not reach U. Look at the digraph shown here. There is a path from A to C, but there is no way I am at C and I can move back to A. So in this digraph, A reaches C, but C does not reach A. Connected graph. A graph G is connected if all vertices in G are reachable from all vertices. Look at the graph G1 shown here. Place yourself at A. Do you have a path to B? Yes. Move from A to D, then from D to C, and then from C to B. Do you have a path to C? Yes. Move from A to D and then from D to C. Do you have a path to D? Yes. It's a direct connection. Do you have a path to E? Yes. It's a direct connection. So this means that all nodes are reachable from A. Now place yourself at B and see if you have paths to all nodes. Yes. So this means all nodes are reachable from B. Now place yourself at C and see if you have paths to all nodes. Yes. So this means that all nodes are reachable from C. Now place yourself at D and see if you can reach all nodes. Yes. So all nodes are reachable from D. Finally, place yourself at E, where you find that all nodes are reachable from E. So this means that for the graph G1, all nodes are reachable from all nodes. So I say that the graph G1 is connected. Now come to the graph G2. Place yourself at A. Do you have a path to B? No. You can only go from A to E and D. But if you are at A, you cannot go to C or B. If you are at B, then A, E and D are unreachable, but C is reachable. So since a few nodes are not reachable when you are at A, this means that in the graph G2, all nodes are not reachable from A. So this means that in the graph G2, all nodes are not reachable from all nodes. So I can conclude that G2 is not a connected graph, or it is a disconnected graph. An easy way to find out if a graph is connected or not is to look at the graph. If you can see the graph in one piece, then it is a connected graph. But if the graph exists as separated fragments in more than one pieces, then the graph is disconnected. The graph G1 exists as one piece, so it is connected. But the graph G2 exists as two different pieces, so it is disconnected. The complete traversal of a disconnected graph is impossible. The extent of traversal of a disconnected graph depends on the node from which traversal starts. In G2, if I start traversal from A or E or D, I can traverse and visit 3 nodes out of 5. But if I start traversal from B or C, I will be able to traverse 2 nodes out of 5. Let's talk about connectivity in a digraph. A digraph G is strongly connected when if U reaches V, then V reaches U. If you have a path in one direction, you should have a complementary path between the same two nodes in the other direction. I leave you to investigate and confirm that the graph G1 shown here is strongly connected. If a digraph G is not strongly connected, but by replacing all directed edges with undirected edges, we get a connected graph, then G is weakly connected. I leave it upon you to ensure and convince yourself that the graph G2 shown here is not strongly connected, but still it is weakly connected. Remember trees, the chapter we just did? A tree is an acyclic connected digraph with n nodes and n-1 edges. Acyclic, it does not have any cycle. Connected, it is in one piece. Digraph, it is a directed graph, directed from the root towards the leaves. What about n nodes and n-1 edges? Let me give you a proof of this. A tree has n nodes. Every node has an edge coming into it from its parent node. And this is true for everybody except the root. So there are n-1 edges. In these two trees shown here, convince yourself that the number of edges is one less the number of nodes. Subgraph. A subgraph H of graph G has a set of vertices that is the subset of that in G and a set of edges that is the subset of that in G. So I have a graph G1 here. Now look at the graph G2. All the nodes that are present in G2 are also present in G1. All the edges that are present in G2 are also present in G1. I can say that the set of nodes in G2 is a subset of the set of nodes in G1. I can also say that the set of edges in G2 is a subset of the set of edges in G1. So this means that G2 is a subgraph of G1. One more thing that I must say here is that G1 is also a subgraph of itself. If you remember set theory, every set is an improper subset of itself. So continuing that thought, I can say that every graph is an improper subgraph of itself. Spanning subgraph. A spanning subgraph H of graph G has the same set of vertices as G and a set of edges that is a subset of that in G. So we have the graph G1. Look at the graph G2. The set of nodes in G2 is the same as the set of nodes in G1. The set of edges in G2 is a subset of the set of edges in G1. So this makes G2 a subgraph of G1. Since the set of nodes is the same in both G1 and G2, G2 is a special kind of subgraph called the spanning subgraph. Spanning tree. A spanning tree of graph G is a spanning subgraph that is a tree. Look at the graph G1. The first step in making a spanning tree is to make a spanning subgraph. For a spanning subgraph, we take all the nodes in G1, but we select only a few edges from G1. So we make a graph G2. Now this is a subgraph and it is a spanning subgraph. It is acyclic and it is connected. But it is an undirected graph. So replace all the undirected edges with directed edges. Before that, select the root node. You can select any node to be the root node. I am selecting A and I am replacing all the undirected edges with directed edges emanating from A or moving away from A. So this is how I place my edges. And now I have in G2 an acyclic connected digraph. This becomes a tree. If you are not convinced, let me rearrange the nodes for you. Actually, this is just a rearrangement of the components of G2. And now you can see that this is a tree rooted at A. Some people might ask, why did I place an arrow from D to C? Why did I not place an arrow from C to D? If you remember, in a tree, every node receives only one incoming arrow. A node cannot have two parents. It cannot have two incoming arrows. So since D already had an incoming arrow from A, the arrow from C to D could not be placed. I placed an arrow from D to C. So this is how you get a spanning tree. Now I will talk about data structures for graphs. The graph is a nonlinear structure and storing it in memory is quite a challenge. There are two approaches for storage of graphs in memory. One method is called the adjacency list method and the other is called the adjacency matrix method. And we will look into each of them one by one. How do you make an adjacency list? This method uses linked structures or the linked list that we saw. For each vertex, maintain a list of nodes that are adjacent to it. So, look at the graph. I have drawn up a table for it. From A, I can go to nodes B, C, and D. From B, I can go to C. From C, I cannot go to any node. From D, I can go to C and E. And from E, I can only move to C. Now, I have a start pointer. It points to nodes of the graph. And each node is placed in a data structure. It has three fields: the node name, the next pointer, and the adjacency list pointer. So this is the data structure for A, and then the next pointer of this node points to the node containing B. The next pointer of this node points to the node containing C. The next pointer of this node points to the node containing D. And the next pointer of this node points to the node containing E. The next pointer of the node containing E is none because these are all the nodes that the graph has. This is my nodes list. Now look at the node containing A. A has three edges. I add a data structure containing two fields, and the adjacency list pointer of the node containing A points to this two field node. The first edge of A goes from A to B. So the first field points to B. See, this data structure is an edge and it goes from A to B. So the node containing A points to this data structure and the first field of this data structure points to B. This is not the only edge that A has. So it points to another data structure. Now this second data structure is another edge from A. It is an edge from A to C. There is another edge from A. So the second data structure points to a third data structure. This third data structure represents an edge from A to D. So if you are at the node containing A and you follow the adjacency list pointer, then you come to the first edge, the edge from A to B, which takes you to the second edge, the edge from A to C, and this takes you to the third edge, the edge from A to D. All the edges of A have now been stored in memory. B has only one edge, so the adjacency list pointer points to just one data structure, and the next pointer of this data structure is none. This is an edge from B to C, so the first field of this data structure points to C. C does not have any neighbors. The adjacency list pointer of the node containing C is none. Move to the node containing D. This has two edges, so the adjacency list pointer points to a two-field data structure. Its first field points to C because this is an edge from D to C. Its next field points to another two-field data structure. Now, the first field of the second data structure points to E because this is an edge from D to E. And the next field of the second data structure is none because D has only two edges. Now we come to the node containing E. E has only one edge from E to C. So the adjacency list pointer points to a two-field data structure, and the first field of this data structure points to C. And the second field, the next field of this data structure is none. Now this is my edges list. I have stored all the nodes of the graph. I have stored all the edges of the graph. And this structure is called the adjacency list for the graph that has been drawn on this slide. The second way of storing a graph in memory is by the use of an adjacency matrix. Here we create a Boolean matrix A of order n by n, where n is the number of nodes in the graph, such that an entry Aij is 1 if I is adjacent to j and it is 0 otherwise. The adjacency matrix for the graph shown here is this matrix. Look at the first row. From A, I can move to B, C and D. So their relevant entries are 1. From B, I can move to C. So in the second row, there is only 1 at the intersection of B and C. From C, I cannot move to any node. So all entries of C are 0. From D, I can move to nodes C and E. So these two entries are 1 and the rest are 0. In the last row, there is only 1 because from E I can only move to C. As you can see, this matrix is Boolean. An important matrix with reference to a graph is its path matrix. The adjacency matrix A is the matrix of all paths of length 1. A squared, which means A multiplied with A, is the matrix of all paths of length 2. A raised to the power m is the matrix of all paths of length m. In a graph of n nodes, the maximum length of a simple path is n. This simple path would be a cycle if it exists. You need to prove this statement for yourself. The first thing that you need to prove is that the maximum length of a simple path is n, and then if such a path exists, it will be a cycle. The path matrix P is a matrix of paths of all lengths present in G, and it is given as P is equal to A plus A squared plus all the way to A raised to the power n. Let us compute the path matrix for this graph. We start with the adjacency matrix and we multiply this matrix with itself to find A squared. This is simple matrix multiplication. How do I interpret this matrix? There are two paths of length 2 from A to C. One is this path from A to B and then from B to C. One is this path, from A to D and then from D to C. A path of length 2 from A to E. Can you see this path? This path goes from A to D and then from D to E. A path of length 2 from D to C. From D, move to E and then to C. Now I have the adjacency matrix and square of the adjacency matrix. Again, using matrix multiplication, I compute A cube. This matrix gives me all paths of lengths 3. Only one entry in this matrix is 1. All the rest are 0. How do I interpret this? There is a path of length 3 from A to C. From A move to D, then from D move to E, then from E move to C. Now I have A squared and A cubed. I will compute A4. Notice that there are 5 nodes in the graph. So the maximum power of the adjacency matrix that I am supposed to compute is A raised to the power 5. Right now I am going to compute A raised to the power 4 with the help of matrix multiplication. And I get a matrix which is all zeros. So this means that there are no paths of length 4. We stop calculating further powers of A when the resultant matrix is all zeros or the resultant matrix is the same as a lower power of A previously calculated. Stop calculating further powers of A if you get a matrix that is all zeros or if you see a matrix that is repeating itself. You've already had this matrix in a lower power. So now I have these 4 matrices, and since A raised to the power 4 is 0, I can judge from this that A raised to the power 5 will also be 0. Now the path matrix is the summation of A squared and A cubed. This is simple matrix addition. The path matrix shows all paths present in the graph. Homework. Friendly Airlines has 9 daily flights shown here. Draw a graph showing all flights, representing each location by the first letter of its name. Store this graph as an adjacency list, storing flight numbers in the edge nodes. Use 3 fields in each edge node instead of 2. Compute the adjacency matrix for all flights. Take row and column elements in alphabetical order. And finally compute the path matrix for friendly airlines. What did we learn today? We were introduced to graph terminology. We stored the graph in memory. And we computed path matrix for the graph. Dear students, please read the book, do the homework, note your questions, and we will talk about them in the online session. And if you have any suggestions, write me an email. Take care. Allah Hafiz.